So let's discuss about the properties of the rational functions. What is a rational function? A rational function is a function r of x equals p of x over q of x, where p and q are polynomial functions and q is not the zero polynomial. Because if q is a zero polynomial, then the function r of x will be undefined. So the domain of the rational function is the set of all real numbers except those for which the denominator q is 0. So that means that when we calculate the domain of a rational function, we must exclude from the domain of the function any number making the denominator of the function equal to 0. How can we find the domain of a rational function? In previous activities, we already discussed how we find the domain of a rational function. So to find the domain, we're going to find the zeros of the denominator, and we're going to exclude those values from the domain. So to find the domain, we basically just look at the denominator of your function, so the expression under the fraction bar, okay? And then you will find the zeros of this denominator. To find the zeros, you will basically get your denominator and you will make it equal 0. You will later solve this equation. And then now we know that this number, -5, is the number that we must exclude from the domain of the function because it makes the denominator of the function equal 0. So -5 must be excluded from the domain of the function. That means if we have a number line, just to visualize, we have here -5. At -5, you will have a discontinuity in the domain. All the numbers to the right of -5 will be in the domain of the function. All the numbers to the left of -5 are in the domain of the function. So the only number that is not in the domain is -5. So your domain in set-builder notation will be the set of all x such that x is not equals -5. And in interval notation, you can say that the domain is from -infinity to -5 union from -5 to +infinity, and you have to use parentheses, everywhere here because -infinity, -5, or +infinity are not included in the domain of the function. So this is how we find the domain of a rational function. The next I want to discuss with you is the asymptotes. So we have in the rational functions horizontal asymptotes, vertical asymptotes, and there are also oblique asymptotes. In this case, I will just put the tension over the horizontal and vertical asymptotes only. So when you have a horizontal asymptote, well, if as x approaches to -infinity or as x approaches to +infinity, the values of r of x, or the rational function, approach to some fixed number L, then the line y equals L is a horizontal asymptote of the graph of R. So basically, here you have a y equals L, a horizontal asymptote in the graph of the function. You see how as x here approaches to positive infinity, y is approaching to the line y equals L. So y approaches to L. Okay, in this case, you see how y approaches to L. So this line y equals L is the horizontal asymptote. On the other hand, here you see how as x approaches to negative infinity, and the function approach to L. So we have that as y approaches to L, then the line y equals L is horizontal asymptote of this function. Now, what about the vertical asymptotes? This is x equals c. So what is a vertical asymptote? If as x approaches some number c, the absolute value of r of x approaches to infinity, or r of x approaches to negative infinity, or r of x approaches to infinity, then the line x equals c is a vertical asymptote of the graph of r. So let's explain this. Let's have a vertical asymptote at x equals c. This vertical asymptote comes from a factor x minus c. And if this factor have multiplicity n, and the multiplicity of this factor in this case is even, then the behavior that you're going to have near to the asymptote would be this one. In this behavior, as x approaches c from the left, y approaches to positive infinity, or as x approaches to c from the right, y also approaches to positive infinity. The other possible behavior here would be like this. So in this one, as x approaches to c from the right, from the left first. As x approaches c from the left, y approaches to negative infinity. And as x approaches c from the right, then y approaches to negative infinity. Now, we have this other case. We have this vertical asymptote x equals c, which is coming from a factor x minus c to the n, and n, the multiplicity of the factor is odd. Then this is the behavior you are expecting to get near the asymptote. This is c. So you will see how as x approaches c from the left, y approaches to negative infinity, or as x approaches c from the right, y approaches to positive infinity. The other possible behavior would be then like this. You know, there is that, of course, the opposite. As x approaches c from the left, y approaches to positive infinity, and as x approaches c from the right, y approaches to negative infinity. So these are, in this case, the behaviors near the asymptotes. Let's see then, sorry, how can we find the asymptotes? So when we read about how we locate the vertical asymptotes, we find that a rational function of x equal p of x over q of x in lowest terms. We have a vertical asymptote x equals r if r is a real zero of the denominator of q. That is, if x minus r, as I was explaining before, is a factor of the denominator q of the rational function r of x equal p of x over q of x in lowest terms, in R we have the vertical asymptote x equals r. So for example, here I give you two examples of how, or two examples to find, the vertical asymptote, if any, of the graph of the rational functions. So in my first case, I have the function f of x equals x plus 3 over x minus 1. If I want to find the vertical asymptote, I know that the vertical asymptote would be a 0 of the denominator. So I will get the denominator, I will make it equal to 0. I will solve for x, and here at x equals 1, I have my vertical asymptote. I want to emphasize something that I believe is very important. There is that the vertical asymptote is not a number, so it's a mistake if we say that the vertical asymptote is 1. The vertical asymptote is the equation of a vertical line, so the vertical asymptote is x equals 1. So the vertical asymptote is not 1. The vertical asymptote is x equals 1. We have this other function, r of x equals x over x squared minus 4, right? The function is already in lowest terms. So I will get the denominator, x squared minus 4. I would make it equal to 0. I will then solve this. I will just factor, it's a difference of two squares, so it's x plus 2 times x minus 2, the factorization of this. So we make now each factor equals 0, so we get x equals negative 2. And then we made the other factor equals 0, so we get x equals positive 2. So here we have then two vertical asymptotes. The first vertical asymptote is x equals negative 2. The other vertical asymptote is x equals 2. So here we have two vertical asymptotes. Are x equals negative 2 and x equals 2. And the behavior that you will have near these vertical asymptotes will be similar to the behavior of this case. Why? Because these vertical asymptotes, right? The behavior will be like the behavior here. And why? Because these vertical asymptotes are coming from factors that have multiplicity 1. So these have multiplicity 1. These two factors have multiplicity 1. So the behavior you're expecting near those vertical asymptotes in both examples is similar to the behavior when the multiplicity is odd. There is here an explanation of how you find the horizontal asymptote or oblique asymptote of a rational function. I will summarize all these explanation in a few words. So basically, first, horizontal asymptote and oblique asymptote are mutually exclusive. So you have either horizontal or oblique asymptote. You cannot have both asymptotes at the same time. As I said, I will just focus my attention in the horizontal asymptotes. And then to know if you have horizontal asymptote and how to find this horizontal asymptote, you have to look at the degrees of the polynomials that you have, the numerator and denominator of the function. So when the degree of the numerator is lower than the degree of the denominator, then the function r is a proper rational function, and the asymptote will be a horizontal asymptote, y equal to 0, so it will be the x-axis, the horizontal asymptote. When the degree of the numerator is greater than or equal to m, then you will have a, in this case, oblique or horizontal asymptote. But as I said, I am not going to pay attention to oblique asymptote now. So we say that if the degree of the numerator is greater than is equal, sorry, the degree of the denominator, so when not equal, then the horizontal asymptote will be the quotient between the leading coefficients of the numerator with the leading coefficient of the denominator. There you will have a horizontal asymptote. Now, if the degree of the numerator is greater than the degree of the denominator in one unit, then you will have an oblique asymptote, and you must find that oblique asymptote by long division of polynomials. Let me then just go and explain this quickly here. We have to find the horizontal asymptote. We have these three functions. In my first function, out of x is equal to 3x over x. When you look at the degree here of the first function, it has degree 1, the denominator have degree 1. So the degree of the numerator is equal to the degree of the denominator. That means that now the horizontal asymptote will be equals to the leading coefficient of the numerator over the leading coefficient of the denominator. So what is the leading coefficient of the numerator? The leading coefficient of the numerator is 3. What is the leading coefficient of the denominator? There is an invisible one here. So the leading coefficient of the denominator is going to be 1. So we will have the horizontal asymptote is 3 over 1. So the horizontal asymptote would be y equals 3. So the line y equals 3 will be the horizontal asymptote in this case. Let's see now, the next function. P of x is equal to 4x squared, over x to the third minus 1. So as you can see, the numerator have degree 2, and the denominator have degree 3. So in this case, the degree of the numerator is lower than the degree of the denominator. So since the degree of the numerator is lower than the degree of the denominator, then automatically we can say that we have a horizontal asymptote. But since this is a proper rational function, then the horizontal asymptote is the line y equals 0, which is the x-axis. And then finally, we have this other function that is h of x equals x to the third minus 8 over x squared minus 5x plus 6. In this case, when you analyze the relation between the degrees, you see how the degree of the numerator is greater than the degree of the denominator. So since the degree of the numerator is greater than the degree of the denominator, then what we have in this case is an oblique asymptote. And if you want to find this oblique asymptote, you must do a long division of polynomials. As I mentioned, I am just focused on horizontal and vertical asymptotes. So you can see later video about how to perform a long division of polynomials if you don't remember this from previous classes. My next example here is given a graph, from the graph of a rational function, and there you have a graph of 3 different rational functions, how to find the main, range, intercept, horizontal asymptotes, and vertical asymptotes for all these functions. Let's start with the first one. So in the first case, domain, I will use interval notation. So you see how you have 2 branches in your graph, and there is an asymptote. It's evident due to the behavior of the graph near the line x equals 2. There is an asymptote at x equals 2. So there is a discontinuity in the domain at x equals 2. So the domain of your function would be from negative infinity to 2 union from 2 to infinity. That would be the domain of this function. Now, we're going to analyze the range of the function. So the range of the function, you see that there is a horizontal asymptote at y equals 1. The graph doesn't show, an intersection with the horizontal asymptote. So the horizontal asymptote becomes a discontinuity for the range of the function. So you can say that the range of the function goes from negative infinity to 1 union from 1 to positive infinity. Intercepts, we have these intercept at 0, 0. There is no other intercept. Horizontal asymptotes, yes. This horizontal dashed line, y equals 1, is a horizontal asymptote. Vertical asymptotes, yes. This vertical dashed line, x equals 2, is the vertical asymptote in this case. What else we know? We know that this vertical asymptote x equals 2 comes from a factor x minus 2 to the power of n, and this n, the exponent, is odd because the behavior near the vertical asymptote suggests that. Let's see the next example here. They say domain. Well, when you analyze the domain of this second function, you see how there is an asymptote at x equals minus 1. The behavior near this vertical dashed line, x equals minus 1, is evident. The behavior near an asymptote is a discontinuity. So the domain goes from negative infinity to negative 1, union from negative 1 to infinity. Now, in this case, all my graph is above the x-axis, right? All my graph is above the x-axis. The graph is approaching to the x-axis. There is no evidence, that the evidence the graph is going to be crossing or touching the x-axis. So it's pretty clear that the x-axis of the line y equals 0 is a horizontal asymptote. So we can say that the range here would be from 0 to positive infinity. You are not including 0, of course, here as part of the range. Intercepts. We have one y-intercept at 0, 2. Horizontal asymptotes. Yes, y equals 0, or the x-axis. You see how they extend the x-axis with dashed lines. Vertical asymptote, yes, is the line x equals -1. That is a vertical asymptote. Let's see the last case. In the last case, I have a function that have 3 branches, right? So when I analyze the domain, I see how there are 2 discontinuities at x equals -2 and at x equals 2. So the domain in this case is from -infinity to -2, union from -2 to 2, union from 2 to infinity. This is the domain. Because we have discontinuities, are their asymptotes -2 and 2. Now the range, we have this bottom part of the graph, that go from -infinity to 0, including 0. Right? Union from now the horizontal asymptote 1 to positive infinity. So there is a gap between 0 and 1. All this region is a gap. We have no function in this gap, right? So you see how, we don't include a gap in the range of the function. So from -infinity to 0, we include 0, so we put a bracket at 0. And then later from 1 to infinity. Intersects, yes, we have an intercept at 0, 0. That is this point, of course. Then we have a horizontal asymptote. That is y equals 1. This line. And then we have two vertical asymptotes. And these vertical asymptotes are at x equals -2 and x equals +2. So these two are my vertical asymptotes. These two vertical dashed lines. Like that, we have done the node analysis of the graph of the 3 rational functions given. In a future video, I will later explain, how we can analyze the graph of a rational function. Thank you for the attention in this video. I hope the video will help you understand better this topic. So see you in a future video.